Ever imagine witnessing the universe in its infancy? Like way back when stars first flickered on and galaxies began to form.
It's incredible to think about, isn't it? That's exactly what we're diving into today.
We're talking about those groundbreaking discoveries from the James Webb Space Telescope, the ones pushing the boundaries of what we know about the early universe.
And specifically, we're looking at supernovae.
Those spectacular stellar explosions. And let me tell you, they're more than just dazzling light shows. You sent in this fascinating article from Science Daily about Webb's findings.
And it's rocking the world of astrophysics.
So to kick things off, can you give us a little background? What makes the James Webb Space Telescope so revolutionary?
The James Webb Space Telescope, or JWST, allows us to see farther back in time than ever before. It's like having a window into the earliest chapters of the universe's history.
Wow, a time machine of sorts.
Exactly.
And according to the Science Daily article, JWST is observing a surprising number of supernovae in the early universe, far more than our previous models predicted. The article mentions that these supernovae are being found at incredibly high redshifts.
Right.
Could you explain what redshift is and why it's so crucial for understanding these distant events?
So imagine the universe is constantly expanding, stretching the very fabric of space itself. As light travels across these vast distances, its wavelength gets stretched as well. This stretching shifts the light towards the red end of the spectrum, hence the term redshift.
Okay, that makes sense.
The farther away an object is, the more its light is redshifted. By carefully analyzing the redshift of light from these distant supernovae, we can determine how much the universe has expanded since that light was emitted. This, in turn, helps us calculate the age of the universe at the time those supernovae occurred.
Wow, so we're basically looking back in time.
Exactly. What's remarkable is that these supernovae are being found at redshifts that correspond to a period when the universe was still in its infancy. It's like we're getting a glimpse of the universe's baby pictures.
Incredible. Now, the article delves into two main types of supernovae, core collapse and type Ia. Could you break down the difference for us?
Okay, so imagine a star significantly more massive than our sun. When it eventually exhausts its nuclear fuel, it can no longer support its own weight. The core collapses in on itself, and with incredible force. This triggers a shock wave that blasts the star's outer layers into space.
So that's your core collapse supernova.
Exactly.
A truly spectacular implosion followed by an equally impressive explosion. So what about type Ia supernovae? They seem to have a different kind of origin story.
They do. Type I supernovae involve white dwarf stars, which are the remnants of stars like our sun after they've burned through their fuel. White dwarfs are incredibly dense. Imagine squeezing the mass of the sun into an object the size of Earth.
It's almost unfathomable how much matter is packed into such a small space.
I know, right? Now, there's a limit to how much mass a white dwarf can handle. If it pulls in too much material from a nearby companion star, it can reach a critical point and ignite a runaway nuclear explosion. That's a type Ia supernova.
So it's like a cosmic tipping point. Add too much mass, and boom, you've got a type Ia supernova.
Exactly.
And these type Ia supernovae are particularly exciting for astronomers, right? They act as what researchers call standard candles.
That's right. Because type Ia supernovae always detonate with roughly the same intrinsic brightness, we can use them to measure cosmic distances with remarkable accuracy. By comparing their observed brightness to their known luminosity, we can calculate how far away they are. Imagine them as lighthouses in the vast cosmic ocean.
Cosmic lighthouses, I love that. It's like having a cosmic ruler to measure the universe.
Precisely. And this is where the JWST's discoveries become truly groundbreaking.
Because it's finding these cosmic lighthouses farther back in time than we ever thought possible.
You got it. And the implications of that are enormous.
This is where I think things get really intriguing. The article highlights the discovery of a core collapse supernova at a redshift of 3.6. Can you put that into perspective for us?
That means this supernova exploded when the universe was just a mere 1.8 billion years old. This is the most distant core collapse supernova ever confirmed spectroscopically.
That's mind-boggling. We're talking about a time when galaxies were just starting to take shape. This discovery is like unearthing a fossil from the earliest epochs of the universe.
It really is incredible, isn't it?
But why should we care about stars exploding billions of years ago? What can these ancient explosions tell us about the universe we live in today?
That's a fantastic question. It goes to the heart of why these discoveries are so significant. Think of supernovae as the universe's grand recycling plants. The intense heat and pressure during these explosions create heavier elements from lighter ones. Elements like carbon, oxygen, and iron, the very building blocks of planets and life itself.
So the atoms that make up our bodies, the earth beneath our feet, even this microphone, they were all forged in the hearts of stars that exploded billions of years ago.
Exactly. Studying these early supernovae allows us to trace the origins of these elements, understanding when and how they were created. It's like piecing together a cosmic family tree, connecting the stars that lived and died billions of years ago to the world we see around us today.
That's incredible. It makes you realize that we're not just observing the universe, we are a product of it.
We are very much part of this grand cosmic story.
But it's not just about looking back, it's about what these discoveries tell us about the universe's evolution. The article specifically mentions a Type Ia supernova discovered at redshift 2.9. Now, this is particularly exciting because it smashes the previous record.
Absolutely. The previous record for the most distant spectroscopically confirmed Type Ia supernova was at a redshift of 1.95. This new discovery at redshift 2.9 places it a staggering 11.5 billion years in the past. And this has significant implications for our understanding of the universe's expansion rate, a topic that's still the subject of much debate and research.
And that's where the real mystery begins. We're not just talking about ancient history here, we're talking about fundamental questions of the nature of the universe itself.
Exactly.
But to unravel those mysteries, we need to dig deeper into what these discoveries reveal about the early universe, a place vastly different from the cosmos we observe today.
A universe full of wonder and secrets waiting to be uncovered.
You mentioned that the early universe was a very different place from the universe we see today. Can you elaborate on that? What was so unique about the stars and galaxies that existed in those early chapters of cosmic history?
Well, one of the most significant differences is the chemical composition of the early universe. After the Big Bang, the universe consisted mostly of hydrogen and helium, the two lightest elements. It was within the fiery furnaces of those very first stars that heavier elements, what astronomers call metals, were forged through nuclear fusion. When those stars exploded as supernovae, they scattered these newly formed elements into space, seeding the interstellar medium from which subsequent generations of stars and galaxies would form.
So these early stars were like cosmic pioneers, enriching the universe with the ingredients for planets, life, and everything we see around us.
Precisely. Now, because those early stars formed from material largely devoid of heavier elements, they evolved differently than stars like our Sun.
So how did this lack of heavier elements impact the way these early stars lived and died? And what can that tell us about the evolution of galaxies in the early universe?
That's a question that astrophysicists are eager to answer, and the JWST is proving to be an invaluable tool in this investigation. You see, the presence of heavy elements can significantly influence a star's lifespan, its internal structure, even how violently it explodes as a supernova.
So by studying these early supernovae and comparing them to their counterparts in the present-day universe, we can start to unravel how the abundance of elements has changed over cosmic time.
Yes, and that's just the beginning. We're on the verge of an entirely new understanding of the early universe, thanks to the unprecedented capabilities of the JWST.
It sounds like we're entering uncharted territory in our understanding of the universe's evolution. What are some of the other mysteries that scientists hope to uncover by studying these early supernovae? What might we find as we continue to push the boundaries of what we can see with telescopes like the JWST?
That's the most exciting part. We're just scratching the surface. The deeper we peer into the cosmos, the more questions arise. Imagine, for instance, finding a supernova so distant that it exploded just a few 100 million years after the Big Bang. Such a discovery would provide invaluable insights into the formation of the very first stars, the so-called population 3 stars, which have long been shrouded in mystery.
Wow. Witnessing the explosive death throes of the universe's very first stars would be truly remarkable. It would be like watching the opening act of the universe's grand drama unfold before our very eyes. And to think, these groundbreaking discoveries are just the beginning for the James Webb Space Telescope. We've only just started to tap into its full potential. Who knows what other cosmic surprises await us as we continue to explore the universe with this revolutionary instrument.
That's the beauty of science. Every answer leads to more profound and intriguing questions.
It really puts things in perspective, doesn't it? These ancient explosions, billions of years in the past.
They played a crucial role in shaping the universe we know today.
And as we're learning, they still hold the key to unlocking some of the biggest mysteries in astrophysics. For example, we've been talking about how Type Ia supernovae serve as these standard candles.
Right, helping us measure vast cosmic distances.
But how does this connect to our understanding of something as fundamental as the universe's expansion rate?
That's a question that lies at the heart of modern cosmology. You see, by measuring the distances to these Type Ia supernovae and comparing that to how much their light has redshifted,
Mm.
well, we can track how fast the universe has been expanding over cosmic time.
So it's like creating a map of the universe's expansion history, using these supernovae as markers along the way.
Precisely. And what's fascinating is that these measurements have led to one of the most profound discoveries in recent decades. The realization that the universe's expansion isn't slowing down as we might expect due to gravity.
It's not.
Nope. It's actually accelerating.
That's mind-blowing. What could possibly be driving this cosmic acceleration?
That's one of the biggest mysteries in astrophysics today. Scientists have attributed this acceleration to a mysterious force they call dark energy, which seems to permeate all of space, counteracting gravity's pull.
So, by studying these distant supernovae, we're not just learning about the life and death of stars, we're grappling with the fundamental forces shaping the universe on the grandest scales.
Exactly. And every new supernova discovery, especially at these high redshifts, provides another data point, another clue that can help us refine our understanding of dark energy and its role in the universe's evolution.
It's like piecing together a giant cosmic jigsaw puzzle,
It is
and we're just starting to find the edge pieces.
a very apt analogy. Now let's delve a bit deeper into how the unique conditions of the early universe influence those early supernovae. Remember how we talked about those first generations of stars formed from material almost entirely devoid of heavy elements?
Right, those cosmic pioneers that forged the first heavy elements.
Precisely. Those early stars lived fast and died young, going supernova in a fraction of the time it takes stars like our sun to exhaust their fuel. Their explosions were likely more powerful too, potentially enriching the early universe with heavy elements at a faster rate than we previously thought.
So these early supernovae were not only creating the building blocks of planets and life, but they were also influencing the evolution of galaxies themselves.
You've got it. And because these early stars had a different chemical makeup, their explosions likely produced different ratios of elements compared to supernovae we observe in the present-day universe.
So by studying the light from these ancient explosions, can we actually determine the chemical fingerprints of those early stars?
Absolutely. It's like cosmic archaeology, analyzing the light from these supernovae to decipher the chemical composition of the stars that exploded billions of years ago. And that can tell us a lot about how the universe transitioned from its simple beginnings to the complex cosmos we observe today.
It's incredible to think that by studying the light from these distant, long-gone stars.
We can piece together the history of the universe and our place within it.
Now, the article hints at the tantalizing possibility of finding even more distant supernova with the James Webb Space Telescope. What would it mean if we could push even further back in time, closer to the very beginning of the universe?
That's the ultimate quest in cosmology, to witness the universe in its infancy, a time when the very first stars and galaxies were forming.
We're talking about an era just a few 100 million years after the Big Bang, right?
Exactly. This is a period known as the epoch of reionization, when the universe transitioned from a hot, dense soup of particles to a cosmos filled with light and the first luminous objects.
It's like the cosmic dawn. When the universe first lit up with stars, what might we learn by observing supernovae from this enigmatic era?
Everything. These early supernovae would provide invaluable insights into the nature and evolution of those very first stars, the so-called population 3 stars, which we believe were significantly more massive and short-lived than stars in the present-day universe. Their explosions would have seeded the early universe with the first heavy elements, paving the way for the formation of galaxies and ultimately everything we see around us today.
So these early supernovae weren't just cosmic fireworks. They were the architects of the universe as we know it.
Exactly. And while we haven't observed a supernova from this early epoch yet, the James Webb Space Telescope, with its unprecedented sensitivity and ability to peer deep into the past, holds the key to unlocking this final frontier in cosmic history.
It's like opening a new chapter in the universe's story, one that has the potential to rewrite our understanding of the cosmos and our place within it. But for now, we have these remarkable discoveries from the early universe, pushing the boundaries of our knowledge and igniting our curiosity about the vastness of space and time. It's awe-inspiring to think about those early supernovae, the ones that might have heralded the birth of the first stars and galaxies. It really highlights how much we're still discovering about the universe's grand narrative. As we delve deeper into these cosmic mysteries, it begs the question, what are the implications of these discoveries for our understanding of the universe and our place within it? Where do we go from here?
That's the beauty of scientific exploration. It's a never-ending quest for knowledge. Each discovery opens up new avenues of inquiry, pushing the boundaries of what we thought we knew. The James Webb Space Telescope is poised to revolutionize our understanding of the early universe, and these supernovae observations, just the tip of the iceberg.
Wow.
As we continue to gather data, we can expect even more surprises, more mysteries to unravel.
I'm particularly intrigued by the possibility of finding those elusive population 3 stars, the very first generation of stars to illuminate the universe. What are some of the challenges in observing these ancient stellar giants?
The challenge lies in their distance and faintness. These stars existed so long ago that their light has been stretched and weakened by the universe's expansion. It makes them incredibly difficult to detect, even with the most powerful telescopes. But it's not just about seeing these stars directly. We can also study the imprints they left on their surroundings.
Ooh.
Their intense radiation would have ionized the surrounding gas, creating bubbles of ionized hydrogen that expanded over time. By mapping these ionization bubbles, we can indirectly trace the distribution and evolution of these early stars.
So it's like using the universe itself as a giant cosmic telescope,
Exactly.
looking for the faint echoes of these ancient stars in the fabric of space-time.
And as we develop even more advanced telescopes and observational techniques, we'll be able to peer even further back in time, closer to the very beginning, perhaps even catching a glimpse of the universe's first moments.
It's exhilarating to think that we're living in an era of such profound astronomical discovery. It's as if we're explorers charting a vast, uncharted cosmic ocean, with each new discovery revealing a new island of knowledge. But with every island we encounter, we realize just how much more there is to explore. This has been an incredible deep dive into the early universe, filled with exploding stars, cosmic lighthouses, and the tantalizing prospect of witnessing the universe's first light. We've journeyed billions of years back in time, and in doing so, we've gained a deeper appreciation for the intricate workings of the cosmos and our place within it. Until next time, keep looking up and never stop questioning the universe and the wonders it holds. All right, so this year's Nobel Prize in Physics, AI. I get it. Seems a bit out there, right? But when I saw this, I knew we had to do a deep dive. This isn't just some physics thing. It gets to the heart of how we understand intelligence itself.
It's pretty mind-blowing stuff when you really get into it.
Totally. We're talking about John Hopfield and Jeffrey Hinton, two guys who basically laid the groundwork for the AI revolution that's, well, kind of happening all around us right now. And get this, Hopfield, he started out as a theoretical biologist.
Yeah, using physics to study the brain. Talk about thinking outside the box.
Exactly. And then you've got Hinton, a computer scientist, drawing inspiration from statistical physics, of all things.
Which is fascinating because it shows you the power of cross-disciplinary thinking. I mean, these aren't fields you typically associate with AI, yet here they are revolutionizing the field. And to think, Hinton also won the Turing Award.
No way. It's like winning 2 Nobels.
Exactly. A testament to the impact their work has had. But I'm sure some of you are thinking, okay, that's great, but what do they actually do?
I'm with you. Let's break it down. So Hopfield, back in 1982, he publishes this paper. Ready for this? It's about creating a physics model of memory.
Groundbreaking stuff. Imagine he basically envisioned the connections between neurons in our brains as physical forces.
Hold on, like magnets.
Exactly. Think about how magnets attract or repel each other to find a stable state. He used similar principles to model how neurons interact and form memories.
Okay, so instead of data being stored in a specific location, like on a hard drive, it's more about the patterns of these connections.
Exactly. And these patterns can be triggered based on similarity, what he called associative memory.
Oh, like how a certain smell can suddenly bring back a vivid childhood memory.
Exactly. It's not about the specific location of the memory, but the connections that trigger it. That's how our brains work.
Wow, that is so cool. But wait, so this physics model of memory, it wasn't just about explaining how our brains work, right?
You're right. This model actually helped physicists understand other complex phenomena in a new light. Things like phase transitions.
Phase transitions. Okay, you're losing me a little.
Imagine ice melting, right?
Yeah.
That change from solid to liquid, that's a phase transition. Hopfield showed how these seemingly unrelated concepts, memory and phase transitions, were actually connected on a deeper level.
Mind-blowing. Like finding a secret passageway between 2 completely different rooms.
Exactly. And that's where Hinton comes in. He took this idea of connections and really ran with it, applying it to the world of computers.
And that's where things get really interesting. But we'll save that part for after the break. So these layered networks we were talking about, they weren't just some abstract theory, right? This was the early days of AI.
Oh, absolutely not. This was leading to some seriously impressive breakthroughs even back then, like image recognition, for example.
Okay, computers learning to see, so to speak.
Exactly. Hinton's networks could be trained to identify and categorize images, and they were shockingly good at it for the time. I mean, really impressive.
Wow, so we're talking about computers actually seeing the world, kind of like we do. But wait, there's more, right? Didn't these networks also have this crazy ability to create?
You're right. One of the things that really blew people's minds was that after you fed these networks enough data, they could actually generate new examples of what they'd learned.
Yeah.
Show them enough pictures of cats, for instance, and they could start to generate their own totally new cat-like images.
It's like those AI art generators that everyone and their dog is talking about these days, but this is decades ago.
It is pretty wild to think about.
It really is. But you're saying this wasn't about, like, perfectly recreating a human brain in a computer, right?
Right, exactly. It's important to remember that these early networks, as groundbreaking as they were still very simplified models of the brain. Hinton actually made this comparison. He said it was like comparing an apple to a planet.
Okay, I kind of see what he means.
They're both round, right. But the level of complexity, totally different universes.
Right, right. Okay, so a good reality check. But even if they weren't perfect brain replicas, this was still a massive step forward.
Absolutely massive. What Hopfield and Hinton did was introduce this idea that, hey, computers can learn from data. They don't have to be limited to just following pre-programmed instructions.
Which seems so obvious now.
Right. But that shift in thinking, that's the seed that blossomed into the AI explosion we're seeing today.
Wow. So everything from ChatGPT to AlphaFold, all of that traces back to these early ideas about layered networks and learning from data.
It all goes back to that core concept.
It's pretty incredible when you think about it.
It really is.
It's not all sunshine and roses, though, right? I mean, didn't Hinton himself actually come out and say he was worried about how fast AI is progressing?
Yeah, he did. And, it's understandable. AI has huge potential for good, but with that much power, well, there are bound to be some risks. It's something we have to think about very carefully.
For sure. You mentioned safeguards. What kind of safeguards are we talking about? What do we actually need to do to make sure this all goes in a good direction?
Well, first and foremost, we have to think about the ethical implications. For example, how do we prevent AI from being used to discriminate? How do we make sure AI benefits everyone, not just a select few? These are big questions that we really need to be grappling with as AI continues to advance.
Big, important questions. It's good to know people are thinking about this stuff. Okay, so potential downsides, check. But there are also already positive impacts happening right now thanks to all of this, right?
Absolutely. And it's not just about having cool new tech toys to play with. AI is already driving really meaningful progress in things like scientific discovery. And those breakthroughs, they're going to impact our lives in a real tangible way.
Like what? Give me an example.
Well, look at astronomy. Astronomers are now using AI algorithms to sift through massive amounts of data from telescopes.
So instead of having, like, a whole team of scientists poring over images for months, the AI can do it in a fraction of the time.
Exactly. And it's not just about speed. Often, the AI is actually more accurate than humans.
Wow.
It means we can identify things like supernovae or potentially hazardous asteroids much, much faster and with more reliability.
That's huge.
Right. Early detection, that's key.
Totally. Okay, so astronomy, that's one example, but this is relevant to other fields too, right?
Oh, absolutely. We're talking medical diagnoses, climate modeling, drug discovery. These are all areas where AI has the potential to analyze information and make predictions with incredible speed and accuracy.
Yeah.
It's really revolutionizing how we approach these challenges.
So, like, having a superpowered assistant helping us solve some of the world's toughest problems.
Exactly.
That's exciting. And it's not just about practical applications either, right? I mean,
Okay.
you were saying something earlier about how this work is also impacting how we understand the human brain itself.
Oh, yeah, for sure. Remember May-Britt Moser, the neuroscientist who won a Nobel Prize back in 2014?
Refresh my memory.
She discovered grid cells in the brain, these specialized cells that basically give us a sense of space. Well, her and her team actually used a modified version of Hopfield's network model to study how these grid cells help us navigate and create spatial memories.
Wait, so they're using AI to study the brain itself?
Exactly. And it's actually helped them make some really important discoveries about how our brains work.
That's wild. It's like using a mirror to get a better look at ourselves, you know?
It really is.
This Nobel Prize, it wasn't just a win for physics or for computer science. It was a win for our understanding of ourselves and our place in this crazy universe.
Beautifully put.
When you really think about it, it's amazing that all of this groundbreaking work, all of these world-changing discoveries, they all started with two scientists looking at the same question from totally different perspectives.
It just goes to show the power of thinking outside the box, right? Connecting ideas from different fields. It's often in those unexpected intersections that the real breakthroughs happen.
It's like that saying, creativity is just connecting things.
That's exactly.
And this Nobel Prize is like the perfect example of that in action. It really underscores how important it is to be curious, don't you think? To be willing to look beyond your immediate field and see how different ideas connect.
100%.
You never know where those connections might lead.
You really don't.
So, as we wrap up our deep dive into the world of physics, AI, and the brilliant minds of John Hopfield and Geoffrey Hinton, I just have one final thought.
I'm all ears.
Think about your own passions, your own interests, what might seem like completely unrelated fields to you. Maybe there are hidden connections there just waiting to be uncovered. Keep asking those questions and stay curious because you never know, you might just stumble upon the next big breakthrough. It's really amazing when you think about it. All of this groundbreaking work, all these world-changing discoveries, they all stem from two scientists who approached the same question from totally different angles.
It really speaks to the power of interdisciplinary thinking, doesn't it? Sometimes the most innovative ideas come from connecting those dots between fields that on the surface you wouldn't think have anything to do with each other.
Totally. Like, there's that saying, creativity is just connecting things.
Yes.
And this Nobel Prize is like the perfect example of that in action.
Absolutely.
Really underscores how important it is to, nurture curiosity.
Definitely.
And that willingness to kind of look beyond just your immediate area of expertise because you never know what those connections might reveal.
Exactly. Exactly.
So as we kind of wrap up our deep dive here into the world of physics and AI and the just incredible minds of John Hopfield and Geoffrey Hinton, I just have one final thought.
Get me with it.
Think about your own passions, your own interests, what might seem like totally unrelated fields to you. Could there be some hidden connections there just waiting to be discovered? Keep asking those questions and stay curious, my friend, because you never know. You might just stumble upon the next big thing. Remember that feeling seeing those first Hubble pictures?
Yeah.
It's like the universe just decided, hey, I'm going to share my photo album.
Right.
And now with JWST, it's even better, sending back even more incredible stuff. But here's the thing.
Yeah.
Even with all that, we're still just scratching the surface of what's out there.
It's true. Yeah. It's like we've been listening to this symphony, but only with a handful of instruments, and now we're about to get the whole orchestra.
Okay, I like that analogy. So walk me through it.
Okay, sure.
What are we missing?
Imagine, like, trying to understand a whole art exhibition, right?
Okay.
But you can only see one color of the paintings. You'd miss so much. The full story, the little things, the hidden stuff. The universe is kind of like that.
Yeah.
To really get it, we got to see it in every wavelength of light.
So it's not just about bigger telescopes. It's about having the right tools for the job.
You got it.
Yeah.
And this Physics World article we're looking at today, it lays out a plan for a whole new generation of telescopes, each one fine-tuned for a specific type of light. And when we put all that data together, that's when it gets really cool.
Okay, so the ultimate collab. The article calls it a great observatory. Is that the idea?
Exactly. It's like an orchestra, but with telescopes, each one playing a part to make this huge symphony of data.
So we have ones for infrared, X-rays, even radio waves, all working together.
Exactly. It's about layering things, getting a richer picture. But just like any big project, there are challenges. It reminds me of, the whole JWST situation.
Oh, yeah.
Groundbreaking, but all those delays, the budget, oof.
Talk about a development cycle, right. But what did we learn from all that?
Well, JWST taught us we need ambition, but also got to be practical. These huge projects, they can easily turn into winner takes all. And then other important missions get sidelined or delayed.
So how do we avoid that in the future? This article talks about a two-pronged approach.
Right, that's key. Yeah.
So is that the answer?
It's a big part of it. So the idea is to invest in those flagship missions, the big ones like JWST, but also, and this is important, smaller probe-class missions too.
Okay, so balance out those home runs with some well-placed base hits.
Exactly. Push the boundaries, but manage the risks and the resources too.
Love this strategy. All right, so let's start with those big swings. What flagship missions are on the horizon?
Well, at the top of the list, a successor to Hubble.
Oh, wow.
Imagine a telescope so powerful, it could directly image exoplanets.
No way.
Earth-sized planets in those habitable zones around other stars.
Hold on, wait. We're not just talking about detecting them indirectly now, right?
Okay.
We're talking actual images.
You got it.
Wow.
But to do that, we need a massive jump in technology, particularly with something called coronagraphs.
Coronagraphs, right. Remind me again what those are.
Okay, so imagine trying to spot a firefly, right?
Okay.
But it's right next to a spotlight. That's what it's like to see a planet next to a star.
Oh, yeah, I see what you mean.
Coronagraphs are like high-tech shields. They block that blinding starlight, so we can actually see those dim planets orbiting around it.
Wow, starlight blocking. No wonder it's a challenge, but that's what makes this so exciting. The possibilities, an actual picture of another Earth. That's game-changing.
For sure. But we can't forget about the rest of the light spectrum, right?
Right, of course.
The article also talks about how important X-ray and infrared telescopes are. In fact, there are two proposed missions, nicknamed Fire and Smoke.
Okay, I see what they did there. Very catchy. So what kind of mysteries are Fire and Smoke going to tackle?
All right, so Fire, that's the X-ray one,
Uh-huh.
would be perfect for studying the most energetic events. Black holes, gobbling up matter,
Mm-hmm.
or those massive explosions when stars are born.
So Fire is all about catching those quick, powerful events.
Yeah, stuff that happens in a cosmic blink.
That's amazing.
And then there's Smoke. That's far infrared.
Yeah.
Perfect for looking through those massive gas and dust clouds, the ones that block our view of star formation.
So Fire gets the fireworks show, and Smoke sees how the stars are born. It's incredible how they work together.
Right.
It's like we're getting a whole new generation of these great observatories, building on what we learned from Hubble, Chandra, Spitzer, all of them.
It is, yeah. And that's not even mentioning the ground-based telescopes.
Oh, right.
They're getting some amazing upgrades, too. They're crucial to this whole orchestra of observatories.
Okay, so we're already talking about groundbreaking science, mind-blowing technology, and we haven't even touched on what's happening here on the ground yet. Tell me more about that.
Ground-based telescopes, those are the ones like here on Earth, right?
Right, yeah.
So how do those fit in when we're talking about seeing things billions of light years away?
That's a good question. So ground-based telescopes, they don't have it easy. They're stuck down here with our atmosphere.
Right.
But they've got other advantages.
Okay, like what?
For one, they can be way bigger, like way bigger than anything we could launch into space.
Okay, now you've got my attention. How much bigger are we talking? This Physics World article mentions a couple of cool projects. There's the 30-meter telescope, for example.
30 meters, the name kind of gives it away.
Right, a mirror that's 30 meters across. Think about all that light it can gather.
30 meters, that's huge. My whole house could fit in that thing.
It really puts things into perspective. And then there's the giant Magellan telescope. It's a different approach, but just as impressive.
Oh,
Instead of one massive mirror, it combines 7 of them, each one over 8 meters wide, all working together. Basically, it's like one giant telescope with a diameter of almost 25.5 meters.
so it's like 7 telescopes in one. That must be some serious engineering.
Oh, absolutely.
But what can these supersized telescopes see that, say, Hubble can't?
It's not always about seeing different things. It's more about seeing the same things, but with way more clarity.
Okay, I think I see what you mean.
Think of it like listening to music on a crappy old radio versus like a top-of-the-line sound system,
Yeah.
These telescopes, they gather so much more light, which means they can see those faint objects, the really distant ones, and the details are much sharper.
So it's all about that resolution, seeing those little details that might tell us something big.
Exactly. And because they're on the ground, they're easier to maintain, easier to upgrade.
Right?
So as new tech comes out, we can implement it faster. Keeps these observatories at the cutting edge.
It's like having a state-of-the-art lab that's constantly evolving. This Physics World article, it mentions something called the Next Generation Very Large Array. That sounds intense. What's that all about?
Ah, that's for radio astronomy, yeah. It's a whole other way of observing the universe.
Radio astronomy. So not even light anymore.
Right, exactly. So picture this. Hundreds of radio dishes spread out over a huge area, all working together to create these crazy detailed images of the radio sky.
Whoa, okay.
This new array would be revolutionary for studying things like pulsars.
Pulsars, right? The spinning neutron stars.
Yep, those are the ones. And even the faint afterglow of the Big Bang itself.
Wait, seriously? We could see that?
It's called the cosmic microwave background radiation, but yeah,
These are
essentially.
mind-blowing. It's amazing all the different ways we've figured out to observe the universe. Each one shows us a different piece of the puzzle. But with all this talk about new telescopes, what happens to the old ones? Like Hubble, Chandra. Are they just going to be retired?
Not at all. As long as they're working, as long as they're doing good science,
Mm-hmm.
they're still super valuable.
Really?
Yeah, even if newer telescopes are more powerful in some ways,
Right.
the older ones, they often have unique capabilities, things that make them irreplaceable.
Okay, that makes sense. It'd be silly to just get rid of a perfectly good telescope, especially if it can still make important observations.
Exactly. And the article even talks about a possible ultraviolet probe mission. It wouldn't be a flagship mission, more like a smaller, focused project,
Okay.
but it can still make huge contributions, studying exoplanet atmospheres or how galaxies change over time.
I like it. It's all about using the best tool for the job, whether it's a massive ground-based observatory or a smaller, more specialized space telescope. But with all these amazing projects in the works, I gotta ask, how realistic is this? This all sounds incredibly expensive.
Yeah, no kidding. Space exploration has never been cheap.
True, very true.
And these new telescopes, we're talking next-level ambition here.
It's a big investment, no doubt. But I think it's important to remember what we get back from that, a
Wow.
deeper understanding of, well, everything. The universe, our place in it.
Investing in our future, like you said.
Exactly.
But it takes time, too, right? I mean, this article mentions these telescopes potentially still going in the 2070s.
Wow, yeah.
That's a timeline most of us can't even imagine.
It's a long game, for sure. But that's part of what makes these projects so incredible. They're not just for us, you know?
What do you mean?
It's about leaving a legacy, a path of discovery for future generations.
It's like planting a tree.
Yeah,
right?
you might not get to enjoy the shade, but you know it'll be there for someone someday.
I like that.
It's a powerful thought.
It really is. It's at the heart of what makes these things so inspiring, I think. Contributing to something bigger, something that'll outlive us all. This quest for knowledge.
And imagine, right, by the 2070s,
Yeah.
we could have pictures of other Earths.
It's mind-boggling.
Maybe even proof of life out there.
Who knows what we'll find?
It's almost impossible to grasp what those discoveries would mean. It changes everything, our whole understanding of the universe.
That's the most exciting part. Those moments where we have to rethink everything we thought we knew.
Those aha moments.
Exactly. The ones that change our perspective make us ask even bigger questions.
So like that feeling when you finally get something you've been stuck on,
Yes.
but on a cosmic scale.
Exactly.
We've talked about the what and the how of these future telescopes. But the big question for me is, what does it all mean?
The million-dollar question.
Right.
What will these discoveries tell us about the universe? How will they change how we see ourselves? No one knows for sure. But one thing's for certain,
What's that?
the knowledge we get from this, it has the power to change us profoundly.
So it's not just about what we find out there in space, it's about how those discoveries change us here on Earth.
Absolutely. Expanding our horizons, literally and figuratively. Inspiring future generations to never stop questioning, to never stop exploring.
Beautifully said. That sense of wonder, of exploration, it's what makes all this so captivating. Thank you so much for taking this deep dive with us. It's been incredible.
It was my pleasure. Remember, keep looking up. Hey everyone, and welcome back for another deep dive.
Hi, everyone.
This time we are going to space again.
Of course, as always.
As always, right?
Mhm.
And we're going to be looking at all the exciting things you can spot in the night sky in October.
Yes.
So sort of a forward-looking
October skies.
October skies, exactly.
Tour.
A tour guide to the October skies.
Yeah.
And we're basing this on the UK Space Agency's blog post all about this.
Right.
So to kick things off, I think a good place to start is planets.
Okay.
Because they are always kind of, they're easy to spot.
Yeah.
And
We're bright.
they're bright and people recognize them and get excited about them.
Yeah.
So, so Saturn, first of all, if you remember from last month's deep dive, we talked about how to find it in the sky. It's still there.
Yes.
In the
It's
southeast.
still hanging out in the evening sky.
In the evening sky.
Yeah.
So that's easy to find. And this month, in October, it's actually going to be near the moon on October 14th.
It will, yeah. Yeah, you'll be able to see them quite close together in the sky.
And that's always fun to see, right? When you can...
Yes, definitely. And the moon will be about 90% illuminated that night, so it will be quite a bright
Oh, wow.
a spectacle.
So it'll be easy to spot.
Yeah, yeah.
What about other planets?
Let's see. Jupiter is actually also going to be up in the sky in the northeast this month,
Okay.
and it will be near Aldebaran, which is the brightest star in the constellation Taurus.
Okay.
So those two will be
So how would people find
hanging out together.
Taurus in the sky?
So Taurus, I see how to describe that best. So if you can find the Pleiades star cluster, which is also actually up in that region of the
All
sky,
right, okay.
Jupiter will actually be trailing behind the Pleiades throughout the month of October.
Okay, great.
So you can watch how they progress across the sky.
Oh, that's interesting. Okay.
But Aldebaran is also very near the Pleiades, so you'll be able to find it that way.
Okay.
It's kind of in that same region.
Okay, great. So
Jupiter, Aldebaran,
yeah.
and the Pleiades.
Yes.
All very close together.
Relatively close.
Yeah.
In the grand scheme of things.
In the grand scheme of things, that's right.
Yeah.
Okay, so that's kind of the quick overview of those easily spottable planets.
Right.
And I actually wanted to talk a little bit more about the Pleiades because they're not just a star cluster.
They're not. They're special.
They're very special.
Yeah.
What's special about them?
Well, first of all, they're very young stars.
Okay.
They're only about 100 million years old, which cosmically speaking is very, very young.
Right, right.
And they are passing through a cloud of gas and dust,
Wow.
which they're actually illuminating.
So you can see
And
that.
you can't see it with the naked eye, but with a larger telescope.
Okay.
Or if you take like a long exposure photograph,
Yeah.
you can actually see this nebula around the stars.
Oh, wow. That's really cool. Okay, so
Yeah, we've got planets, we've got a star cluster. What about galaxies? Anything interesting happening in the galaxy world?
yes. Well, we can't forget Andromeda, which is our closest galactic neighbor.
Yeah, Andromeda.
It's a large spiral galaxy, and it's actually much bigger than you might think.
Okay.
It actually spans about 6 full moons in our sky.
Wow, really? 6?
6 full moons, yeah.
I
But
had no idea.
we can only see the bright core with the naked eye.
Okay.
The rest of it is too faint. But it's just amazing to think about how massive it is, just right there.
Yeah, and it makes you feel very insignificant
It really does.
when you think about it.
It puts things into perspective, that's for sure.
It really does. So for people who want to try and spot Andromeda
Yeah.
this month, how would they go about doing that?
So one of the easiest ways is to find the constellation Cassiopeia,
Okay.
which is a pretty distinctive W shape in the sky. And Andromeda is located not too far from Cassiopeia. And then you can also use the constellation Perseus, which is in that same region of the sky, as a guide as well.
Yeah.
So if you can find Cassiopeia or Perseus, you're in the right neighborhood to look for Andromeda.
Perfect.
Yeah.
So that's Andromeda. Now, I did want to ask you about something else that's up in the sky this month, something a little bit different, and that is a comet.
Yes.
Because
Comet time.
comet time, right?
Yeah.
Always exciting.
So we have Comet C 2023-A3. It's also known as Tsuchinshan ATLAs, if you want to, impress your friends.
Which one should we go with?
I would go with C 2023-A3 because
Okay.
Tsuchinshan ATLAs is a mouthful.
It is a mouthful.
But it will be visible to the naked eye
Okay.
in October.
Wow.
And this comet's actually pretty cool because it survived a close encounter with the sun
Oh, wow.
earlier this year. So
So I've been through it.
it's been through it and it's still going.
It's a survivor.
It's still putting on a show for us. Yeah, it's a survivor.
So how are we going to see that in the sky in October?
Yeah. So the best time to catch it is going to be from around the 16th to the 20th of October.
Okay.
And you'll want to look to the west after dark. And it should be near the bright star Arcturus.
Okay.
So again, we'll post some sky maps to help people find their way around.
Okay, perfect.
Yeah.
Now, I wanted to ask you about
Yeah.
meteor showers.
Yes, we've got...
Because October is
Oh.
a good month for that.
It is a good month for meteor showers. We've got 2 that are kind of the big ones this month. One is the Draconids, and they peak around October 8th and 9th.
Okay.
And then we have the Orionids, which peak on the 21st and 22nd of October.
Okay.
So,
What's the difference?
so the Draconids, those fragments are traveling at about 13 miles per second,
Okay.
which is actually quite slow.
For a meteor?
For a meteor, yeah, that's considered slow. And then the Orionids, those fragments are zipping along at about 40 miles per second.
Oh, wow. That's quite a difference.
Yeah, it's a big difference.
Why? Why the big difference?
Yeah. Well, they just come from different comets, which are traveling at different speeds. So the Draconids, those are fragments from Comet Giacobini-Zinner, and then the Orionids, those come from the debris left behind by Halley's Comet.
Okay. So it's all relative to
It's all relative.
whatever their parent body is doing.
Exactly.
Okay. Interesting. So we've got all this stuff happening in the sky that we can see from,
From our backyards.
from our backyards. What
Yeah.
about
Yeah.
missions? What's happening in the world of space missions this month?
Yeah, so there's actually a couple of really cool missions that are either launching or are ongoing this month.
Okay.
So the European Space Agency has their Hera Ray mission,
Okay.
which is actually a follow-up to NASA's DART mission.
Oh, right. Yeah, the one where they smashed
They smashed into a
spaceship into an asteroid.
Yes, an asteroid.
Yeah.
Yeah, so
Fascinating.
Hera is going to go and actually study the aftermath of that impact. So it's going to be a rendezvous with the asteroid, which is Dimorphos, and it's going to be looking at things like the size of the crater, what the composition of the asteroid is like,
Okay.
and just gathering all sorts of data about that impact.
To see if it actually worked, I guess.
To see if it worked, exactly.
That's amazing. So cool. And then the other mission, which I'm really excited about, you mentioned, is the Europa Clipper.
Yes.
And that's going to Jupiter's moon.
It is, yeah. Going to Jupiter's moon Europa, which is a really interesting target, I guess, for space exploration at the moment.
Yeah.
Because it has this, we think, this vast salty ocean beneath its icy surface.
Yeah, we always talk about Europa, right?
Yeah. It's a prime candidate for finding life.
Yeah. So what's Europa Clipper going to do?
So Europa Clipper is going to be studying Europa in a lot of detail,
Okay.
trying to figure out, what is the composition of that ocean? How deep is it? Is there any, interaction between the ocean and the surface?
Wow. And how do you even begin to figure that out?
Right. That's the question.
Like if it's under ice?
So it has all these instruments, like ice-penetrating radar. It can, look through the ice
Wow.
to the ocean below. It has spectrometers, which can analyze the composition of the surface and maybe even any plumes. If there are any plumes erupting from the ocean, it can analyze the composition of those.
Okay.
And it has a magnetometer to study Europa's magnetic field, which can actually tell us a lot about the ocean as well.
Wow. So when's that launching?
That one is actually scheduled to launch this month.
Oh, wow.
So it's going to launch, and then it's going to take about 6 years to get to Jupiter.
Okay.
So we've got a bit of a wait.
Yeah, we got a bit of a wait, but I'm sure it'll be worth
It'd
it.
be worth it.
So much cool stuff going on this month. We've got the planets to spot. We've got the comet. We've got meteor showers. And like you said, we've got these really, really exciting missions happening as well.
Yeah, October is a good month.
It is a really good month to get out there and do some stargazing. So I think that about wraps up this month's deep dive. Thank you so much for joining me and for sharing all of this incredible information with us.
Oh, it's my pleasure, as always. Happy to be here.
And thank you to everyone listening. Don't forget to check out the show notes for all the links to the UK Space Agency blog post and all that kind of stuff. And we'll see you next time for another deep dive.
Okay, so have you ever tried to find a dime in a huge pile of pennies?
Oh, yeah.
It's almost impossible, right?
Yeah.
Well, imagine trying to find 7 dimes not just stacked, but scattered across the entire universe, and they're all in a perfect line.
Wow.
That's basically what we're talking about today. A super rare cosmic alignment of 7 galaxies, all lined up perfectly behind this massive galaxy cluster.
It's like the universe is playing a giant game of billiards out there.
Totally. And the coolest part is that this lineup, it's called the Carousel lens.
Hmm.
And it's way more than just a cool image. It's actually giving us a peek into one of the biggest mysteries in the universe, dark matter.
Yeah, dark matter. The universe is an invisible giant.
Right.
We can't see it, but we know it's out there pulling on everything.
So, okay, let's back up for a second. How does a bunch of galaxies in a line help us study something that we can't even see?
But it all comes down to this really incredible thing called gravitational lensing.
Okay.
Imagine a bowling ball on a trampoline.
Yeah.
It makes a dip.
Right.
Well, picture that on a cosmic scale.
So you're saying this galaxy cluster is about 5 billion light years away, is like that bowling ball sitting on the trampoline of space-time.
Exactly. It's massive gravity warps the fabric of space-time around it. And when light from even more distant galaxies travels past that warped space-time, it gets bent.
So it's like a lens.
Exactly.
It bends the light.
It magnifies and distorts that light for those more distant galaxies.
So instead of seeing a single point of light from those really far away galaxies, we see multiple images.
Exactly. And in the case of the Carousel lens, because that alignment is so precise, those warped images are arranged in a symmetrical, mirrored pattern around that cluster.
Hence the name Carousel.
Exactly.
That's really cool. But this is also incredibly useful for scientists, right?
Oh, yeah.
Because it gives them something really important when it comes to studying dark matter.
You see, mapping dark matter is really tough. It's like trying to figure out the shape of a mountain just by feeling around in the dark. But with the Carousel lens, we had these 7 background galaxies, all acting like beacons shining through that darkness.
So each one of those warped images is like another measurement point for the cluster's dark matter.
Exactly. And because the lensing is so symmetrical, those measurements are really precise.
Wow.
It's like having 7 perfectly placed spotlights all illuminating the dark matter structure of that cluster.
So finding this kind of alignment is kind of like winning the cosmic lottery.
Yeah.
But how did astronomers even find this thing in the first place?
It was a multi-step process that took human ingenuity and a lot of computing power.
Wow.
The story starts back in 2019 with the Dark Energy Survey.
Okay.
They were using this incredibly powerful telescope to map a huge chunk of the sky, collecting data on millions upon millions of galaxies.
So they had all this data, I mean, millions of galaxies.
Yeah.
How do we go from that to finding this incredibly rare alignment?
Right.
Did they have like a grad student looking at pictures of galaxies for years?
Not quite.
Okay, good.
This is where computers become really important.
Okay.
They used a supercomputer to go through all of that data,
Okay.
looking for these unusual patterns in the way that galaxies are arranged.
So like looking for that symmetrical shape.
Exactly.
Okay.
And what they found was that the computer flagged this specific cluster with the 7 background galaxies.
Wow.
There's a potential gravitational lens.
So it's like finding a needle in a haystack.
It really is.
But the story doesn't end there.
No, it doesn't.
Right.
It gets even cooler.
Okay.
A separate team in 2021 was using data from the Dark Energy Spectroscopic Instrument,
Okay.
or DII.
Yeah, so.
And DII doesn't just capture images, it actually analyzes the light from those galaxies,
Okay.
breaks it down into a spectrum.
Okay. Why is that important?
Well, think of it like a fingerprint.
Okay.
A galaxy's spectrum can tell us things about its chemical makeup, its distance from Earth, how fast it's moving.
So they were able to confirm, using the spectral data, what the first team found just by looking at images.
Exactly. The DSI data provided independent confirmation that this really was a group of 7 galaxies being gravitationally lensed by that massive cluster.
Okay, so they had 2 sets of data now saying this is real.
That's right.
This is really happening.
But the best part
Okay.
came from the Hubble Space Telescope.
Okay, I was going to say, we got to get Hubble in here.
Hubble had to make an appearance.
Of course, those images are always incredible. So what did Hubble show us about this?
Hubble captured these absolutely stunning, crisp-clear images of the cluster.
Okay.
And there they were, those 7 distant galaxies, warped and magnified into multiple images, all arranged in this perfect mirrored pattern.
That's amazing.
It's like looking through a kaleidoscope at the depths of the universe.
Yeah, it really is. So it's beautiful, but these images weren't just beautiful, right? They actually helped scientists learn even more about this system.
Exactly. They provided definitive proof of this lensing effect.
Wow.
And they allowed scientists to study the system in incredible detail.
So we've talked about how this discovery was made, but let's talk about why this is such a big deal.
Okay.
What is so important about mapping dark matter?
Right. So dark matter makes up the vast majority of the universe's mass,
Okay.
about 85%.
85%. So that means everything that we can see, all the stars and planets and galaxies, that's just a tiny fraction of what's actually out there.
It really is mind-boggling.
It is.
But here's the thing.
Okay.
Even though dark matter makes up most of the universe,
Yeah.
it doesn't play by the same rules as normal matter.
What do you mean?
It doesn't emit light.
Wait.
It doesn't reflect light.
You can't see it.
We can't see it.
Okay.
It's totally invisible to all of our telescopes.
So we know it's there. We know it's affecting things with its gravity.
Yeah.
But we have no idea what it is.
It's like there's an elephant in the room,
Okay.
and you can only see its footprints.
I like that. Okay.
That's why this carousel lens discovery is so important.
Okay.
It's giving us a way to see the invisible.
Because each one of those lensed galaxies is like a pin on the map showing us where the dark matter is.
Precisely.
Okay.
And by understanding how dark matter is spread out,
Uh-huh.
we can start to understand some bigger questions about the universe.
Like what?
Like, how did galaxies even form in the first place?
Okay.
What's the role of dark matter in how galaxies evolve?
So it's like this invisible scaffolding
Yeah.
holding everything up.
Yeah, a great analogy.
And this is giving us a glimpse into that.
Exactly. And there's even more to it.
Okay.
Remember that discrepancy we talked about?
About the expansion of the universe.
Yes, the Hubble tension.
Right? Where we have 2 different measurements and they don't line up.
Right, and the carousel lens could actually help us with that too.
Okay. How?
So imagine if a supernova...
A really big exploding star?
Exactly.
Okay.
Imagine if a supernova were to occur in one of those background galaxies.
So we've got the supernova going off in one of those really distant galaxies. What happens then?
Well, because of the lensing, we wouldn't just see one supernova.
Oh,
We'd see multiple images of it.
Oh, really?
And each of those images would arrive at Earth at a slightly different time.
Because the light's traveling a different distance.
Yeah, because it's taking a different path through that warped space-time.
Like a cosmic delay.
Exactly, a cosmic delay.
Okay.
And so by measuring those tiny time delays
Okay.
and taking into account everything we know about the carousel's mass distribution,
Including the dark matter.
especially the dark matter,
Okay.
scientists could get a really precise measurement of the distance to those galaxies.
And that helps us figure out how fast the universe is expanding.
That's the key right there.
Okay, so this 1 in a billion alignment,
Yeah.
this cosmic carousel,
Right.
it could actually help scientists solve this big disagreement about how fast the universe is expanding.
It's a real possibility.
Wow. So this just goes to show how important it is to keep looking up and seeing what else is out there.
Absolutely.
Because we find something new every time.
It's true. And this carousel lens,
Yeah.
it didn't just come out of nowhere.
Right.
It came from a much larger data set.
The Dark Energy Survey,
Exactly.
which has found hundreds of millions of galaxies already.
Hundreds of millions, and it's still going.
And this is just one interesting thing they found.
Imagine what else is out there.
So you're saying there could be more of these perfect alignments
Oh, absolutely.
hidden within all that data.
Just waiting to be discovered,
Each one of them a potential key to understanding dark matter.
and maybe even more.
That's incredible.
Yeah, it really makes you think.
It really does. So what does it all mean? What's the takeaway here?
I think it tells us that the universe is full of surprises,
Yeah.
and we've only just scratched the surface.
There's so much more out there we don't even know about.
Exactly. It's a humbling thought.
It is, but it's also pretty inspiring.
It should make you want to go outside, look up at the stars,
Yeah. And just imagine what else is out there.
and maybe, just maybe,
Yeah.
there are more of these cosmic carousels out there, each one holding the key to understanding the universe a little bit better.
That's an amazing thought.
It really is.
Well, that about wraps it up for this cosmic deep dive. I hope you enjoyed exploring the mysteries of the universe with us today.
Me too.
Until next time, keep looking up.